Hi everyone, welcome back. Today we're going to be learning about the mean value theorem. The mean value theorem says that if f of x is continuous on the closed interval ab and differentiable on every point on the interior of ab, then there's at least one point on the open interval ab which f prime of c equals f of b minus f of a over b minus a. To illustrate that question, I'm just going to draw a quick sketch of a graph. Let's say we have a graph that looks like this. This is A, B, and I guess A comma f of A, and B comma f of B. So all the theorem says is that there's at least one point on this interval where the slope is the same as the slope of that point right there. So if I just, you can kind of see around there it's going to have the same slope, and around here it's going to have the same slope too. So in this case, there's two spots where we have the same slope as the average slope over the whole thing. That's why it's called the mean value theorem. We say, what's the average slope from point A to point B? The average slope is this slope right here. And there's 2 points in that interval that have the same slope. Now, the theorem says that there's at least one. So there's other cases where I could draw an interval like this. Oh, let's get blue. So if I look at the two endpoints, the slope from endpoint 1 to B is 0. It's the same thing here, A comma f of A and B comma f of B. The slope from the beginning to the end, or the average slope, is 0. There's at least one point on that interval where it also has a slope of 0. And if we talk specifically about the slope of 0, that's called Rolle's theorem. You don't need to know that for your AP test, but if you take calculus in college, they will probably address Rolle's theorem, because Rolle's theorem is just the same thing as the mean value theorem, except we have to have a horizontal line. With the mean value theorem, it can be slanted like we have over here. So that's what the mean value theorem says. I tried changing my color setup, so hopefully it's a little bit more interesting. I like these colors a little bit more. So we have example 1. It says, show that the mean value theorem is true for f of x equals the square root of x on the closed interval 0 to 4. And I shouldn't say that it's true, but we want to show that the conditions are met. So don't say this, we want to say the conditions are met. So we should know by now that the square root of x looks something like this. And I want this from the interval from 0 to 4. And this point is 4 comma square root of 4. That's 2, 4. All I did was substitute 4 into my square root of x. So this is the interval I want. I just have to show that the conditions are met. So all you need to show is that two things. The first thing is that we have a closed interval. The closed interval is 0 to 4. The graph is continuous. And it's also differentiable on the open interval 0 comma 4. Now the reason why I would say it's differentiable on the open interval 2, 4 is because there is no left-hand limit here. There's no left-hand limit because the square root of 4 only exists from 0 to infinity. But if I use an open interval, any point you pick close to 0, I can get closer. Like if you say I want to say, oh, well, 0.01 is as close as you can go. I can say I can go a little bit further than that. I can go to 0.001 and get on the left-hand side of your point. So I can always get closer so we can find a derivative there. That's why it's important that we say that it's differentiable on an open interval, because it would not be differentiable on the closed interval. On this example, we want to show that it doesn't satisfy. And if I did want to take this one step further, I could say at some point on the interval, uh, 0, 4, f of x has a value of f prime equal to, let's look at our overall slope. The slope, the mean slope here is from point 0, 0 to 2, 4. 4 minus 0 over 2 minus 0. At some point, we're going to have a slope of 2. And we could find that point, but that's not what the problem's asking us to do. If I were to take a guess, it would be somewhere around there, but my graph isn't perfect. So now in this case, we want to show whether the functions satisfy or don't satisfy the conditions of the mean value theorem here. Actually, on this problem, both of these are not going to satisfy the conditions of the mean value theorem. For problem A, we have f of x equals the square root of x squared. Well, we all know that the square root of x squared is equal to x. And I should be able to find the slope of that everywhere. It should be continuous everywhere. But I actually do have a small problem. Because of the way that this problem is written, this x squared will always be a positive number. So even if you were to pick like -3, for example, you wouldn't get y equals -3. Let's see what would happen. If I pick -3, I'd have -3 squared, and then I would take the square root, I would have +9. The square root of +9 is 3. So what's happening here is not y equals x, it's actually y equals the absolute value of x, because the square is making every term positive. Well, now let's look at the absolute value of x. The absolute value of x looks something like this. And if I consider that on -2 to 2, well, there is a point right here. Well, -2 to 2 is going to have a slope of 0, but I do have a problem right here. It's not differentiable at that point. So that's the point where I would have a slope of 0, but there is no derivative because there's a corner. Absolute value of x has a corner, so this is not differentiable. Not differentiable. At x equals 0. So there's a problem because I can't use the mean value theorem if it's not differentiable. Now let's look at the piecewise function. My first thought on a piecewise function is there's going to be something funky at this point right here, because otherwise I have a linear function of 2x plus 1 and a linear function of -2x plus 1. So it's quite possible that it's not continuous at this point. So let's just see if it is continuous. Let's look, what is f of x? Let's find, well, let's write it like this. Let's find the limit as x approaches 2 from the left, and the limit of x approaches 2 from the right. Approaching from the left, I'm going to have 2 times 2 plus 1, 5. Approaching from the right, I have negative 2 times 2 plus 1, which is going to be negative 3. So since the limit on the left and the right are not equal, this is not continuous. So I can't use the mean value. It does not satisfy the conditions of the mean value theorem because it's not continuous. If we think about our examples, let's think about, I guess let's just look at an example of why discontinuous would not be okay. Let's look at 1 over x. 1 over x actually has a positive slope everywhere. But if I consider these 2 points here, it will have a negative slope. Since it's not continuous, it breaks the rules of the mean value theorem. Even though I can pick 2 points on the graph, since it's not continuous, these 2 points have a negative slope, even though the slope everywhere on the graph of y equals x is positive. Now we're going to consider, we're actually going to find the point that has the slope of the mean value theorem. So in example 3, we have let f of x equal the square root of 9 minus x squared on the closed interval negative 3 to 3. We want to find the point where the tangent is parallel to the segment constructed by connecting the endpoints. So the equation f of x equals the square root of 9 minus x squared is actually a semicircle. If you don't remember that, that's fine. You could graph this, but the graph looks something like this. 1, 2, 3. 9 minus 3 is going to be 0, and 9 minus negative 3 squared is going to be 0. Oops. And going to look something like this. And you could imagine that if I did 9 minus 0, I'd have the square root of 9, which is why I have this point here as 3. So I've got a graph that looks like this. You could probably just guess by looking at it where the point is that we have a tangent line that's parallel to connecting the endpoints. So connecting the endpoints is going to be right here. The slope of that is just going to be, so we're going to find the slope between those 2 endpoints now. The slope between those 2 endpoints is going to be 0 minus 0, that's both my y's are 0, over 3 minus negative 3. We get 0 over 6, or 0. So what we have to do is find the point where the slope is 0. Now, the way I do that is by finding the derivative. Since the derivative tells me slope, I'm going to find f prime of x here. And just so we know that this as well, we have 9 minus x squared to the 1/2 power. That makes it so I can use the chain rule. All I did there was rewrite this. So if I use the chain rule now, I have 1/2, leave the inside alone, times the derivative of the inside. The inside is negative x squared, so I have times negative 2x. So those 2's cancel, and I'm left with negative x over the square root of 9 minus x squared. So I want to find where this slope is 0. Now remember, if I have a fraction like this, all I really have to worry about is when the numerator is 0. Because when the numerator is 0, the whole thing is 0. 0 divided by anything is 0. As long as we make sure that we're defined in the denominator, we'll be okay. So we're just going to say, when does 0 equal negative x? Well, x equals 0. The only thing I should do is double check to make sure that point exists. We'll say, if x is 0, is that point okay? So let's just say, so now all I should do is plug in that point real quick to see if it works. If x is 0, we would have 0 over square root of 9 minus 0, which is just going to be 0 over 3, 0. So that point was correct. The only thing I was checking there to make sure that the denominator was not 0 as well. If it was 0, then we'd have a problem. But that's something you can usually just do in your head real quick. So the actual question asked, find the point where the tangent is parallel to the segment constructed by connecting the endpoints. What I found was the x value, where it's going to be parallel. Now I just need to plug that into the original equation to find the y value. So x is 0. Y equals square root of 9 minus 0 squared, 3. So the answer to the question is 0, 3. Now we're going to think about just what does the mean value theorem mean in real life. Example 4 says the applications of the mean value theorem. We're going to check, or it says you checked your speedometer while you were driving on the highway and you were going 50 miles per hour. A little while longer, you checked again and you were going 70 miles per hour. What does the mean value theorem tell us about this situation? Well, I don't know what my average speed was. I don't know if I was going 50 miles for most of the trip and then just stepped on it at the end to go 70, or maybe you were going 70 miles most of the time and you actually slowed down for a little bit because there was a cop or something like that, but you like to go 70 miles an hour. All I know is that at one point I checked my speedometer and I was going 50 miles per hour. Okay, at some point I was going 50 miles per hour. So I don't know what the time was. It doesn't say anything about the time. At some point later, I checked it again, and I was going 70 miles per hour. So at another time, I was going 70 miles per hour. All I know is that at some point I have to cross the mean value theorem. Or sorry, the mean value. So the mean value between 70 and 50 is 60 miles an hour. So the mean value theorem just says at some point we went from 50 to 70 miles. At some point I went 60 miles an hour. It's just impossible for you to jump from 50 to 70 without accelerating through 60 miles an hour. Now, realistically, you probably crossed this threshold tons of times. You probably went fast, and then you slowed down again, and then you went fast again. Depending on how long your trip was, you probably crossed that line tons of time, but the mean value theorem just says we went 60 miles an hour at least one time. Okay? All we're saying is, at some point, we drove at 60 miles an hour. And there's a couple things I glossed over. I glossed over the graph being continuous and being differentiable. So the reason it's continuous is because you, in a car, you can't just jerkily change speeds. You can't go so fast that you're suddenly going backwards. Okay? Cars don't work like that. So the graph of speed is continuous and it's differentiable everywhere. Acceleration is smooth. You don't have a jumpy acceleration when you're in the car. If you step on the gas as hard as you can, you're going to accelerate at some rate that's measurable. And you can also, even if you slam on the brakes, you're going to decrease at a measurable acceleration too. So we have a couple definitions here. The first definition just says, it's the definition of increasing and decreasing. Well, the definition that you would probably understand is that increasing means it's going up. So if I have a parabola like this, it's increasing from here to here, just because the graph is going up, and then it's decreasing here. Let's see what the actual definition says. The definition says, let f be a function defined on the open interval I, and let x and x1 and x2 be any 2 points on I. The first definition says that f is increasing on I. If x1 is less than x2, that means that f of x1 is less than f of x2. It just says if I've got 2 points, x1 and x2, then f of x1 is less than f of x2 because it's going up. If I want to look at decreasing, we say we have point x1 and x2. F of x1 is now greater than f of x2 because it's higher. We haven't talked too much about corollaries in this class, but a corollary is just a really easy to prove theorem. It's usually a theorem that can be proved in just 1 or 2 steps. So the corollary in this example here just says, let f be continuous on AB and differentiable on the open interval AB. If f prime is greater than 0 at each point on AB, then it's increasing. And if f prime is less than 0 on each point, it's decreasing. Example 5, I'm just going to do 2 quick examples of finding when a graph is increasing or decreasing. I started with a fairly easy problem. I would hope that most of us know that f of x equals negative 3x plus 4 is decreasing everywhere because it has a slope of negative 3. But let's do the calculus here to show where it's decreasing. F of x equals negative 3x plus 4. F prime of x equals negative 3. No matter what value of x I pick, there is no x in f prime. So since f prime is negative 3, there's no place to substitute x in. This is decreasing from negative infinity to infinity. B is a downward facing parabola that's raised 3 points above the x-axis. So I know it's going to look like this. I do have an idea of where it's increasing and where it's decreasing, but let's go through the calculus steps here. So all I'm going to do is find f prime of x equals negative 4x. Since the graph is going to be increasing when the slope is positive, I don't have anything to solve for here. I can just say that if x is negative, so when x is less than 0, I'll have a negative times a negative is positive. The graph will be increasing. And the graph will be decreasing at x is greater than 0. And at x equals 0, there's a maximum. It's neither increasing nor decreasing. So that's it for this problem. Example 6, we want to determine where f is increasing and decreasing for this function here. Now we have a cubic function. This is going to be a little bit more interesting. I don't exactly know what it looks like, but cubic functions can look something like this. I don't know exactly where those points are. I'm just drawing a quick sketch of that because that's what a cubic function could look like. It might be increasing everywhere, but it's probably not. That would be a boring problem, and I don't think that we would use something like that in this example. It could be, but this is my idea. If I wanted to, I could graph it to get an idea of what that looks like. So I'll do that real quick. So that's what the graph looks like. Pretty similar to what I have there. That was just my guess of what it would look like. So let's do the calculus to find where it's increasing and decreasing. rather than just guessing or using the calculator to tell us min and max, let's use the calculus here. So again, I want to find when the slope is either positive or negative. So let's find the derivative of f of x equals x cubed minus 3x. So the derivative is going to be f prime of x equals 3x squared minus 3. So I want to find when that is positive or when that's negative. I think the easiest way to solve this would be to find when it's 0, because we can't go from positive to negative without crossing the x-axis. So let's say 0 equals 3x squared minus 3. This will tell us our critical points like we talked about last class. 3 equals 3x squared. I can divide both sides by 3. And I get 1 equals x squared. That means my critical points are at plus or minus 1. So that means that this maximum here, and again, I got this by looking at the graph, so this is kind of cheating by knowing what the graph is going to look like, but my critical points are at plus or minus 1. So now I just have to pick points in between those two critical points to see if the graph is increasing or decreasing there. So the graph in this example is probably going to be decreasing if I'm less than 1. But let's check a point. So let's check to see if we want to check the slope. So I am going to check f prime. We're going to check f prime of negative 2. I'm going to check f prime of 0. And I'm going to check f prime of 2. And I'm picking those points just so I can see is going to be the same along that whole path or on that whole side of the critical point. So f prime of negative 2 is 3 times negative 2 squared minus 3. That's going to be negative 2 squared is 4. 4 times 3 is 12. 12 minus 3 is positive 9. F2 is going to be the same thing. 3 times 2 squared minus 3 is 12 minus 9 again. So let's just find 0 now. We have 3 times 0 minus 3 is negative 3. So the graph is going to be increasing. The graph is increasing here because I have the positive slopes. And it's decreasing here because I have a negative slope. So to answer the question, f is increasing from negative infinity to negative 1 and from 1 to infinity. And it's decreasing from negative 1 to 1 and that's the answer to that question. So a corollary to this says if a function has the derivative f prime equals 0, it's a constant function. So it says if f prime of x is 0 at every point, then it must be a constant. And that is a quick thing to prove, because if we pick any 2 points, the derivative formula stems from the slope formula. So if I pick any 2 points, y2 minus y1 and x2 minus x1, we're saying if the derivative is 0 everywhere, well, the only time that the derivative is 0 is if y2 equals y1. That's the only time that I'll subtract the numerator and get 0. Remember, the denominator doesn't help me find zeros. So the only time that that can happen is if y2 and y1 are the same, and this is saying at each point. So that can only be possible if I have a constant. That's the only time my slope is going to be 0 across. See, again, it's called a corollary because it's very easy to prove. The corollary here, functions with the same derivative differ by a constant. If f prime of x equals f prime of g at each point on the interval I, then there's a constant c such that f of x equals f of g for all x in the interval I. All this is saying is if I have the exact same derivative everywhere, the only thing that could change is if I have a different constant. Let's say I had the derivative of f of x squared, or f of x equals x squared. The derivative is 2x. Well, if I had g of x, there's lots of other problems that would give me the same derivative, lots of other functions, but they have to be x squared plus some number. Because when I take a derivative of a constant, it goes to 0, and I get g prime of x equals 2x. So in this example, we are going to look at antiderivatives. Antiderivatives are a huge topic, but they're not going to be until I think chapter 5 or 6. They're a big topic in calculus. We talked about it at the beginning of the year. There's 3 big topics in calculus. The first is limits. The second is what we're doing now called derivatives. The final topic we'll do at the end of the year is called integrals, or antiderivatives. So in this case, we want to find the antiderivative. We know we have a function whose derivative is 3x squared minus 6x. I want to know, what was that original function? Well, the way you find that is just, when we say, what were the steps that got us here? We brought the power down. Well, bringing the power down is the same as multiplying by that power. Well, in this case, we have to increase the power by 1. And we have to divide by that number, since the opposite of multiplying is dividing. So I already had a 3. Let's write it like this. I have to divide by that 3. Because if I brought the power down, I need that 3 to go away. Let's do the same thing here. Minus 6x, I'm increasing the power by 1. And I have to divide by that power. Because normally I would multiply that power, I have to go backwards now and divide by that power. But there's also one other number. I don't know what that number is. It might be 0. But there's another number because when I took the derivative of this number here, of c, that went to 0. Okay? Normally we just don't write it. But I'm thinking, well, what if there was a number there? So I'm going to simplify this up some. F prime is going to be x cubed minus 3x squared plus c. And I just want to figure out, what is c in this problem? Well, I want the original function to pass through the point 1, 2. So I have an x and a y. So all I have to do is plug those points in now. So we have 2 equals x cubed minus 3x squared plus c. Well, we know that x is 1, and we're solving for c. So I'm just going to stay blue to work a little bit faster here. So I have 2 equals 1 minus 3 plus c. 1 minus 3 is negative 2. If I add 2 to both sides, I get c equals 4. So that means that the original equation had a value of c equals 4. That means my original equation was x cubed minus 3x squared plus 4. I should have wrote it like that. So that's called an antiderivative. We just said that the derivative of the antiderivative is the original function for all x's in the domain. So we're going to do one final problem here. Example 8 says, find the velocity and the position of a free-falling object that starts at an initial height of 0 It has an initial velocity of 0. Acceleration due to gravity is negative 9.8 meters per second squared. It doesn't look like you have much to work with, but they do tell you acceleration. And we know acceleration is the derivative of velocity. So if I take a step backwards, I can probably figure out what was the antiderivative. What was v? And I'm going to write v of t. I'm going to call acceleration a of t. So what was the derivative that got us here, or what was the function that got us this derivative? Well, I just have negative 9.8 t, and I have to consider, well, there might have been a constant that got us here. I do know that the initial velocity was 0, so the initial velocity would be if t equals 0. So if I wanted to figure that out, I would say v of 0 has to equal 0. So in this case, c is 0. So this is the velocity function. The velocity function is just v of t equals negative 9.8 t. Now if I want to find the position function, we've been calling that s of t. It's just going to be the antiderivative of v of t. That means we're going to increase the power of t by 1. We're going to have t squared and negative 9.8 t squared over 2. Since I raised the power of 2, I have to divide by 2 to go backwards. I could simplify that sum. Let's just do, oh, and I do have plus c still. And I'm going to call that c2. Since I already used c before, I don't want to get them confused. Let's simplify that to negative 4.9 t squared. So I'm going to find again, what is the initial velocity? It's going to be the same thing here. Negative 9.8 0 squared over 2 plus c2. When is that going to be 0? It's going to be 0. This will all 0 out. C of t has to be 0 again. Or sorry, c2 has to be 0 again. So my position function is s of t equals, let's see, negative 4.9. I just did that in the calculator. Negative 4.9 t squared. If that is a little bit tricky for you guys right now, that's okay. We're going to move into antiderivatives in a little while. So if this isn't quite clicking for you yet, that's okay. We're going to do more with this later. That's all I have for you today. Thanks for watching.